1986, seven cosmic theorists, later dubbed the Seven Wardens, publish a result that fits no map. The Silver River Galaxy is moving, not merely expanding along with the Cosmos Expanse, moving 627 kilometers per second in a specific direction. This is not drift and not chance. It is the coherent motion of our galaxy together with thousands of others towards something massive, invisible, and located in the part of the sky where astronomy cannot properly look. Today we'll break down what exactly is pulling us, why for 40 years we could not see the source, and what the 2023 data say about whether this chain of attraction has finally come to an end. Let's begin with the map. Any astronomical sky survey, from the mid-20th century Redstone Sky Register to modern digital surveys like Hartwell Survey and Deep Horizon Survey, contains the same problem. A band 10 to 20 degrees wide along the galactic plane, where data are either absent or distorted beyond all use. This is the hidden band. The name is not a metaphor. Sky surveyors literally avoid observing in that direction because the results are unreliable. The reason is technically simple. We are inside the disk of the Silver River Galaxy. Gas, interstellar dust, hundreds of billions of stars in our own galaxy, all of it blocks the view. Optical light from distant galaxies is absorbed and scattered by dust long before it reaches a telescope. To grasp the scale, imagine a world map where all of Westmark, part of Northreach, and part of Southvale are covered by an opaque blot. You can see Highland Union, you can see Suncoast, you can see East Realm, but an entire continent is missing. You know something lies behind the blot, but what exactly? You cannot see. Roughly 20% of the sky, for standard optical astronomy, effectively does not exist. 20% is not some fringe edge. It is a band that runs through the center of the sky vault. It slices every galaxy survey straight through the middle. Every catalog contains this rupture, and it is there behind the strip of dust and stars of our own Silver River Galaxy that the most massive structure in our nearby cosmos is hidden. Back to the Seven Wardens. Graham Mercer, Naomi Ellery, Cedric Halewood, Martin Kersey, Julian Pritchard, Owen Hartley, and Caleb Fenwick. In the mid-1980s, these seven measured the velocities of roughly 400 elliptical galaxies. The method, the Faber-Jackson relation, a classic of observational astrophysics. How does it work? The velocity dispersion of stars inside a galaxy is tied to its luminosity. The more massive the galaxy, the faster its stars move within it, and the brighter it shines. Know the luminosity, and you calculate the distance. Know the distance and the redshift, and you calculate the peculiar velocity, the galaxy's actual motion relative to the overall cosmological expansion. The Hubble expansion pushes everything away from everything else. The universe stretches, and galaxies recede from one another. But layered on top of that expansion, galaxies can have their own velocity under the gravitational pull of massive nearby structures. That extra velocity is called peculiar, from the Latin peculiaris, meaning one's own, distinctive. The result was unexpected for everyone, including the paper writers themselves. Galaxies within a radius of several hundred million light-years were not moving chaotically, as one might expect from random gravitational interactions. They were moving coherently, in one direction, toward a point in the Carpenter constellation, a small southern constellation most stargazing enthusiasts have never even heard of. That point is hidden behind the galactic plane. Halewood called it the Grand Draw. The mass required for such an attraction is on the order of 5 times 10 to the 16th solar masses. That is the combined mass of tens of thousands of galaxies. The distance, about 250 million light-years. The speed, 627 kilometers per second. For comparison, Earthhaven circles the day star at about 30 kilometers per second. The day star circles the center of the Silver River Galaxy at about 220 kilometers per second. Our galaxy, together with everything inside it, is hurtling 21 times faster than Earth-Haven's orbital speed, toward a point that cannot be seen. The problem? It is impossible to look there directly. The hidden band. This created a strange situation in science. Cosmic theorists knew that something massive lay in a specific direction. They had calculated its position mathematically, but they could not see the object, because our own galaxy stood between us and it. Let's read the original. The Seven Wardens paper appeared in Celestial Research Letters in 1986. The title was blunt: Spectroscopy and Photometry of Elliptical Galaxies, a large-scale streaming motion in the local universe. Large-scale coherent motion in the local universe. The paper writers are cautious in their wording. They speak of a flow and a center of attraction, but do not claim to know the nature of the source. For 10 years after publication, there were attempts to find the physical object behind the hidden band. Optical telescopes were useless. Dust absorbs visible light. But there are other ranges in which dust is transparent, or nearly so. Radio waves. For radio waves, interstellar dust is like glass is for visible light. They pass straight through with almost no loss. Neutral hydrogen, the most common element in the universe, emits a characteristic line at a wavelength of 21 centimeters. Radio telescopes can detect that line. X-rays. Hot gas between galaxies and clusters is heated to tens of millions of degrees and shines in X-rays. X-rays pass through dust. Orbital X-ray telescopes can see galaxy clusters where optical telescopes see only the stars of the Silver River Galaxy. The near-infrared range. Not perfect, dust still absorbs part of the radiation, but vastly better than visible light. At wavelengths of 1 to 2 microns, you can see galaxies that are completely hidden in optical observations. The first breakthrough came in 1996. Maris van Elston was a Southridge-born sky surveyor of Dutch descent, a specialist in the hidden band. She used the Stonefield Array in Suncoast, one of the largest radio telescopes in the Southern Hemisphere, famous from the film The Dishpan about receiving signals from Odyssey 11. The Stonefield multi-beam survey made it possible to systematically map galaxies behind the dust lane of the Silver River Galaxy. The result? Beyond the hidden band, roughly where the calculations of the Seven Wardens had pointed, there really was a galaxy cluster. The Mason Cluster, named after the Carpenter constellation in which it lies. Distance, about 200 million light-years. Mass, on the order of 10 to the 15th solar masses. This was the moment when a mathematical point became a physical object. But here the data begin to diverge from the simple model. The Mason Cluster is massive, but not massive enough to explain the full speed of the Silver River Galaxy. According to the calculations of Van Elston and her fellow researchers, Mason accounts for roughly 44% of our velocity. Less than half. Where does the other 56% come from? This is where the original model stops fitting. The Seven Wardens had assumed a single source of attraction, one massive object pulling everything around it. But reality turned out to be more complicated. In 2006, a group led by Trevor Colby of Pacific State University published an analysis of galaxy motions at greater distances. They found that the flow does not end at Mason. Galaxies behind Mason, at distances of 400 to 500 million light-years, are moving too, in the same direction, towards something even farther away. That something is the Marlowe Cluster, the largest concentration of mass in the observable nearby cosmos. Distance, about 650 million light-years. Mass, an order of magnitude greater than Mason's. The Marlowe Cluster had been known for a long time. Edwin Marlowe discovered it back in the 1930s. But its role in the dynamics of the local Cosmos Expanse became clear only in the 2000s. The model grows more complex. Mason pulls us. But Mason itself is flying toward Marlowe. And we are not simply flying toward Mason. We are flying toward the common center of mass of a system in which Mason is an intermediate station, and Marlowe the next node. It is like a current river. Imagine this. The observer is drifting along a river and feels the current carrying them. The observer thinks there is a falls ahead, a single source of pull. But as they draw closer, it turns out the falls are only a rapid, beyond which the river goes on, and around the next bend, another rapid. A chain of attractions, not a single source. In 2014, Warren Keel of Pacific State University, the same Tully for whom the Tully-Fisher relation for measuring distances to spiral galaxies is named, published a map that changed the scale of understanding. Broad heaven, in Hawaiian, immeasurable heavens. Keel and his group used data on the motions of 8,000 galaxies to reconstruct the velocity field in a volume with a radius of about 500 million light-years. The result? All these galaxies, including the Silver River Galaxy, including Mason, including dozens of other clusters, are part of one gigantic structure, the Broadheaven supercluster. The size of Broadheaven is about 500 million light-years across. Mass, on the order of 10 to the 17th solar masses. That is 100,000 galaxies. The grand draw is not a separate object, but the central region of this supercluster, the zone into which matter flows from all sides. But Keel's map showed something else important. Broadheaven borders other superclusters. On one side are dense walls of galaxies flowing toward a common center. On the other, emptiness, a gigantic region of lower density where there are almost no galaxies. This asymmetry matters because gravity works both ways. A massive structure pulls, but the absence of mass also matters. If there is a great deal of matter on one side of the observer and little on the other, the observer will move toward the denser region. Not because the void pushes, but because the dense region pulls more strongly than the rarefied one. In 2017, Daniel Roslin of Kingsbridge University and his group published a paper that added a new dimension to the picture. They discovered a structure they called the twin drift void. Repeller comes from the English repel, to push away. But this is not repulsion in the literal sense. It is a void, a region where the density of matter is far below average. It does not physically push us. It simply does not pull, while the opposite side does. Roslin showed that to explain the direction and magnitude of the Silver River Galaxy's velocity, it is not enough to consider only the attraction of Mason and Marlowe. One must also account for the fact that on the opposite side from us lies a gigantic void, the so-called oceanic void, or the twin drift void. It is as if the observer were standing on the slope of a hillside. On one side, a ridge pulling with its gravity. On the other, a drop, a low veil. The ridge pulls, the veil does not. The observer moves toward the ridge, not only because the ridge pulls, but also because on the other side there is nothing to hold them back. This is not a riddle and not a mystery. It is a model. We are pulled from one side and not held from the other. Attraction plus absence of resistance. Simple physics, complicated geometry. Roslin's work was met with caution. It is one thing to measure the speed of attraction toward a massive object. It is another to measure the contribution of a void. A void does not emit, absorb, or scatter. How do you measure the influence of what is not there? Roslin's method was the reconstruction of a three-dimensional velocity field. If you know the motions of thousands of galaxies within a volume, you can reconstruct the density distribution causing that motion. Low density in one region and high density in another create a gradient that explains the direction and magnitude of the flow. The data showed that the contribution of the void to our speed is comparable to that of the Marlowe Cluster. Not supplementary, comparable. This changed the way people thought. Before Roslin, void mappers built maps of the cosmos from luminous matter, from galaxies. After Roslin, it became clear that maps of the voids are no less important. Voids shape flows the same way mountain ridges shape rivers, not by attracting the water, but by creating the relief through which it runs. The cosmic web is not merely clusters of galaxies joined by filaments. It is walls, threads, and knots, with vast, empty regions lying between them. And those empty regions are not neutral. They are asymmetric, and that asymmetry creates additional velocity components. Let us name who first grasped the scale of it. Graham Mercer and Cedric Halewood in '86 did not know that the Grand Draw was only the first link in a chain. They thought they had found the source. It turned out they had found the first signpost. Maris van Elston in '96 found a physical object behind the dust. The Mason cluster became proof that the calculations of the Seven Wardens were correct, but she did not know about the Marlowe cluster as the dominant source of the additional velocity. Warren Keel in 2014 drew the map of Broadheaven, showed that we are part of a supercluster 500 million light-years across. But Daniel Roslin in 2017 showed that the map was incomplete. Without the repeller, the model gives the wrong direction of motion. Each research scholar closed off one fragment. Not one saw the whole. The full picture began to come together only toward the end of the 2010s. And even now, it is unfinished. And then Starstreams Four data appears. The year 2023, the largest catalog of peculiar galaxy velocities, more than 56,000 measurements. For comparison, the Seven Wardens worked with 400 galaxies. In 37 years, the sample grew by more than a factor of 100. The methods changed as well. The Naomi-Ellery-Jackson relation for elliptical galaxies was supplemented by the Keel-Fisher relation for spirals. Measurements of Type 1a supernovae as standard candles were added. They make it possible to determine distances with an accuracy of 5%. Data from the Edgar Northam Space Telescope expanded the sample to distant galaxies. And, in the latest versions, data from the Continental Space Agency's Astera astrometric satellite, which measures the positions and motions of 1 billion stars in our galaxy and makes it possible to refine the calibration of the entire distance scale. Warren Keel and his group update the map of matter flows with each new data release. The result of recent years is discouraging for those who hoped for a simple model, but reassuring for those who prefer a difficult truth to a simple myth. The flow structure is more complex than attractor plus repeller. Additional nodes of attraction appear, ones that do not fit into a model of two dominant sources. Intermediate voids appear, creating local deviations in the flows. The flows are not linear. They branch, accelerate, and slow depending on the local matter density. The cosmic web turned out to be exactly that, a web with knots, threads, and voids on every scale. Not a tree with a single trunk and branches, but a network in which every node influences every other. A concrete example. On the scale of roughly 400 million light-years, Starstreams Four detects a flow moving neither toward Marlowe nor away from the oceanic void, but in a third direction, toward a structure that has not yet received a generally accepted name. This does not cancel out the contribution of Marlowe or the repeller. It adds yet another vector to the total motion. A three-component model replaces the two-component one, and there is no guarantee that a four-component model will not replace the three-component one in 5 years. What does this mean in practice? We are flying toward the Mason cluster. Mason is part of the flow toward Marlowe. Marlowe is probably part of a flow toward something even more distant. The twin drift void pushes from the other side. The voids between structures create additional pressure gradients. It is a chain, and we do not know whether it has an end. Or rather, the data does not yet allow us to see the end, which is not the same thing. A press release and a paper are not the same thing. Let us examine both. The scientific papers on Starstreams Four phrase it with extreme care. Additional components of peculiar flows have been detected on scales exceeding 600 million light-years, not explained by previously identified structures. News outlets write, "The Cosmos Expanse is sucking our galaxy into the unknown." The first is the result of data processing. The second is a metaphor for clicks. The difference is fundamental. Here is what the data actually shows. The hidden band is not a mystery and not a conspiracy. It is a technical limitation. We are inside the disk of the galaxy and cannot see through it optically. It is like trying to make out a house on the far side of the street from a window when a bookcase stands in front of the window. The bookcase is not hiding the house on purpose. The bookcase is simply there. But the scale of the problem deserves a separate discussion. 20% of the sky is not merely a stripe without data. It is a stripe through which the key directions of void mapping pass. The grand draw lies behind it. Part of the Marlowe Cluster lies behind it. The wall in the Serpent Crown region is partly obscured. The structure, sometimes called the Grand Cluster Wall, passes through the hidden band and emerges on the other side, but its middle remains unseen. This is not accidental. The galactic plane passes through the center of the sky vault, and the largest structures of the nearby cosmos tend toward the same range of latitudes. The bad luck is geometrical, but the consequences are physical. Concrete attempts to solve the problem proceeded along 4 lines. The first is radio astronomy, the Maris van Elston method. The 21-centimeter line of neutral hydrogen. The advantage, dust is completely transparent. The drawback, surveys are slow. Each point in the sky must be observed for a long time to build sufficient statistics. Stonefield Multibeam is a program that took several years and covered part of the hidden band in the southern hemisphere, but not all of it. The northern hemisphere is covered more poorly. The second direction is X-ray astronomy. The X-Scout Observatory, a German X-ray satellite of the 1990s. Then Skylance, an American orbital observatory operating since 1999. Then Newton Crest, a European X-ray telescope. The hot gas between the galaxies of a cluster emits in X-rays. X-rays pass through dust, but X-ray telescopes have a small field of view. They see the sky through a straw. A complete survey of the hidden band in X-rays would require decades of observing time. Partial surveys exist, and they have found several clusters. But completeness is still far from 100%. The third avenue is the near-infrared range. The Twin Sky Atlas survey is ground-based in the 1 to 2 micron band. Farview is space-based in the mid-infrared. Night glow is space-based in the near-infrared. Infrared light passes through dust far better than optical light, but not perfectly. At distances beyond 300 million light-years, infrared galaxies drown in the foreground glow of stars from the Silver River Galaxy. The problem is not dust. The problem is the bright foreground stars that wash out the faint, distant galaxies. The fourth avenue is the newest one, radio continuum and next-generation surveys. The South African Deep Horn Array Radio Telescope, a precursor to the Square Mile Array, is already delivering data. The first results reveal previously unseen galaxies deep inside the hidden band. The Australian South Grid Array adds data for the southern sky. When the Square Mile Array becomes fully operational, it will provide a survey with sensitivity hundreds of times greater than Stonefield Multibeam. In theory, that should be enough to close the hidden band. In practice, construction is ongoing and not yet complete. The first phase of scientific operations will begin no earlier than the end of this decade. A complete survey of the hidden band in radio continuum and in the neutral hydrogen line is work still underway. Every galaxy found is one more fragment of the puzzle. But the number of missing fragments is unknown. There is another version, not popular with a broad audience, but well-grounded among universe modelers. Some believe that the very notion of the grand draw as a single structure, as one object that pulls, is outdated. The attractor is not an object. It is a zone in the space of flows where lines of motion converge. A mathematical center, not a physical body. The Mason cluster lies near this zone, but is not the zone itself. The difference is subtle, but fundamental. If the attractor is a zone rather than an object, then searching for a source of attraction is meaningless. The pull is distributed across the walls and filaments of the cosmic web. There is no single culprit, there is architecture. An analogy, a whirlpool in the current river. A whirlpool is a region where streams of water converge. It has a center, a speed, a size. But there is no whirlpool object, no solid body that spins the water. A whirlpool is a property of the flow, not an object within the flow. The same is true of the Grand Draw. The Seven Wardens in '86 were looking for an object. Maris van Elston in '96 found a cluster near the calculated center, and everyone decided the object had been found. But data from the 2000s and the 2010s showed that the Mason cluster is one of the web's nodes near the center of the flow. Not the only source, one of many. That changes the question itself. Instead of what is pulling us, it is more accurate to ask, what is the structure of the flow in which we are moving? The first question assumes a single cause. The second assumes a distributed system of causes. Science spent 37 years moving from the first question to the second. This is a pattern, and it repeats at every scale. The same logic works on smaller scales. Individual galaxies fall toward clusters. Clusters move toward superclusters. Superclusters move toward the walls and nodes of the cosmic web. At every level, there is an attractor, a local center of pull. For a single galaxy, the attractor is the nearest cluster. For a cluster, a supercluster. For a supercluster, a node of the web. The question is not whether the Grand Draw exists. The question is whether it is the final point in the chain or only another link. And here the data give an unexpectedly clear answer. The standard model of cosmology, lambda CDM, predicts that on scales larger than several hundred megaparsecs, the Cosmos Expanse should be homogeneous. This is the principle of homogeneity, one of the axioms of modern cosmology. If the principle is correct, the chain of attraction ends. At some scale, the flows vanish, peculiar velocities fall to zero, and only pure Edgar Northam expansion remains. The Starstreams Four data still do not reach that scale. They cover a volume out to 600 to 700 million light-years. The principle of homogeneity predicts convergence on a scale of about 1 billion. The gap between data and prediction is several hundred million light-years. It is precisely in that gap that surprises may be hiding. But there is also a troubling signal. Several large structures, the Titan Wall, the vast ring, exceed the theoretical size limit for structures allowed by the principle of homogeneity. If these structures are real, the principle of homogeneity needs refinement. If the principle of homogeneity is imprecise, then the chain of attraction may be longer than the standard model predicts. That is a subject for a separate analysis. Stop. The numbers fail to match somewhere else. 20% of the sky is blocked. That means the map of flows beyond the hidden band is partly extrapolation. We interpolate data from both sides of the band and assume there are no surprises in between. Mathematically, this is called smoothing. We take the density of galaxies to the left of the band, the density to the right, and assume that somewhere in between the value lies in the middle. It sounds reasonable. But Maris van Elston showed in '96 that behind the band, there was an entire cluster hiding there. One no one had predicted, and one that was not in the middle between neighboring data points. Mason was invisible and turned out to be the key to 44% of our velocity. One structure, one cluster, and 44% of the explanation. What guarantee is there that no other such surprise is hiding there? The direct answer? None. Radio and X-ray help, but coverage is incomplete. Not every part of the hidden band has been scanned with sufficient sensitivity and resolution. The square-mile array will improve the situation radically. Its sensitivity is hundreds of times greater than Stonefield multibeam. but construction is not yet complete. Meanwhile, the hidden band remains the largest blank spot in nearby cosmology. Not at the edge of the observable Cosmos Expanse, not beyond the event horizon, right here, within a few 100 million light-years. A blank spot not because of a lack of technology, but because we live inside a structure that blocks the view. The irony is this: to understand where our galaxy is flying, we have to see what our galaxy itself is hiding. A separate question is the precision of the measurements. 627 kilometers per second. That is the speed of the Silver River Galaxy relative to the relic radiation. It is determined from the temperature dipole of the relic background. In the direction of motion, the photons are slightly hotter because of the Doppler effect. In the opposite direction, slightly colder. The temperature difference is about 0.003 of a degree Kelvin against a mean temperature of 2.725 thousandths Kelvin. Tiny, but measurable. The first to see it was SkyProbe in the early 90s. Far Measure refined the figure in 2013 to high precision. We know the speed well, with an uncertainty on the order of 1%. The direction, too, to within fractions of a degree. The problem is not measuring the total speed. The problem is splitting that speed into components. Because 627 kilometers per second is a sum, the sum of the pull of Mason, Marlowe, the push of the oceanic void, the local motion of our home cluster toward the maiden cluster, the rotation of the Silver River Galaxy around its own center, and a multitude of smaller components. To break that sum into its terms is a task that depends on the completeness of the galaxy catalog, on the precision of their distance measurements, on the model of dark matter distribution, and yes, on the completeness of the data beyond the hidden band. Each model gives its own percentages. The model of 1996, Mason, 44%. The model of 2007, Marlowe dominates. The model of 2017, a repeller is needed. The model of 2023, additional nodes are needed. Each update of the data changes the proportions, and each model depends on the same bottleneck, a 20% strip of sky where the data are lacking. Let's look at the dates. 1986, the discovery of the anomalous velocity. The Seven Wardens calculated the direction and magnitude, but did not see the source. 1996, the first look through the dust. Maris van Elston found the Mason Cluster, a physical object exactly where the calculations had pointed. 2014, the map of the supercluster. Warren Keel showed Broadheaven, a structure 500 million light-years across, of which we are a part. 2017, the dipole repeller. Daniel Roslin added a void to the model, one that pushes from the other side. 2023, detailed flows with nodes. Starstreams Four showed that the model is more complex than attractor plus repeller. 37 years of work. Each decade, a new layer of complexity. Each explanation, not a refutation of the previous one, but an expansion of the frame. The Seven Wardens were right. We are flying. Maris van Elston was right. There is a cluster there. Warren Keel was right. We are part of a supercluster. Daniel Roslin was right. We are being pushed as well. But each truth turned out to be partial. This is not an error and not a weakness of science. It is its mechanics. Each generation of instruments sees a little farther and a little more precisely and discovers that the previous map was an approximation. The Redstone Sky Register could not see through the dust. Stonefield did. Stonefield could not see the repeller. Roslin's flow reconstruction did. Starstreams 4 sees farther and finds additional nodes. The square-mile array will see farther still. What it will find, we do not know. But if history teaches anything, it will find something the current models do not predict. And every decade, the same fundamental problem. 20% of the sky we cannot properly look into. 20% behind which the next link in the chain may be hiding, or behind which there may be nothing new at all. We do not know. And until the square-mile array is operating at full capacity, we will not know. Let us sum it up. The grand draw explains 44% of our speed. Marlowe, about another 48. The repeller pushes. Starstreams Four adds nodes. The chain grows longer with each new survey. Each decade, one more link. The principle of uniformity says, there is an end. Somewhere on the scale of several billion light-years, the flows must vanish, and the Cosmos Expanse must become the same in every direction. But we have not yet reached that scale with the data. And the most interesting part is what is hidden by our own galaxy. Names, dates, documents. Graham Mercer, Naomi Ellery, Cedric Halewood, and 4 others. 1986. Maris van Elston, 1996. Warren Keel, 2014. Daniel Roslin, 2017. 40 years of work, from a mathematical point inferred from indirect data to a 3-dimensional map of flows with repellers and nodes, and 20% of the sky still closed off. This is not a mystery, it is an unfinished map. The largest blank spot is not at the edge of the visible Cosmos Expanse, not beyond a black hole's event horizon. It is right here, within a few 100 million light-years. 20% of the sky through which we are learning to see, slowly, method by method, telescope by telescope. This is a solution, not a mystery, but there is one more aspect rarely discussed: dark matter. All calculations of attraction, Mason, Marlowe, the repeller, are based on the assumption that dark matter is distributed roughly the same way as visible matter. Where there are many galaxies, there is much dark matter. Where there is a void, there is little. It is a reasonable assumption, but it has not been directly proven. Dark matter does not emit, absorb, or scatter light. We see it only through its gravitational influence, through the way it bends the paths of galaxies and deflects the light of distant sources. If dark matter is distributed unevenly, not in the same way as visible galaxies, then the map of flows may be completely different. A concrete example: suppose that beyond the hidden band, there is a concentration of dark matter without a corresponding number of galaxies. That is possible. There are models in which dark matter forms clumps that have not yet pulled in enough gas for stars to form. Dark clusters, without galaxies, without gas, without X-ray emission, only gravity. Such an object would be invisible across every band: optical, radio, X-ray, infrared. It could be detected only through its influence on the motion of surrounding galaxies. But if it lies behind the hidden band, we do not see the surrounding galaxies well enough to notice the anomaly. This is not a conspiracy theory. It is the boundary of our knowledge. We assume that dark matter follows the visible matter because everywhere we are able to check, it does. But beyond the hidden band, we cannot check. There is another factor as well: dark energy. Dark energy is what makes the Cosmos Expanse expand with acceleration. It acts on large scales, countering gravity. On the scale of galaxy clusters, several million light-years, gravity wins and the clusters hold together. On the scale of superclusters, hundreds of millions of light-years, dark energy begins to matter. Broad heaven stands at the boundary. It is large enough for dark energy to affect its dynamics. In billions of years, broad heaven will probably come apart. The galaxies at its edges will be carried away by the expansion of the Cosmos Expanse. But right now, we are inside the flow. We are flying toward the center of broad heaven, to the region where the density of matter is above average. And while we are flying, we are part of the structure. When the structure falls apart, we will become part of something else, or nothing. This is a timescale of billions of years. For practical purposes, it does not matter. But for understanding the picture, it matters greatly. We are not merely flying toward a point on a map. We are taking part in a process that determines what the cosmos expanse looks like on the largest scales. And that process depends on what lies behind the 20% of the sky we cannot see. One more detail, the history of science. The Grand Draw is not the first case in which sky surveyors discovered something important in a direction that is hard to observe. At the beginning of the 20th century, Edwin Marlowe, the very one after whom the cluster is named, was trying to determine the position of the day star in the Silver River Galaxy. He used globular clusters as markers, bright objects visible across great distances. The problem? The center of the Silver River Galaxy lies in the direction of the Archer constellation. There, the density of stars and dust is at its maximum. Marlowe saw globular clusters around the center, but not the center itself. He had to reconstruct the center's position from indirect evidence. Sound familiar? 50 years later, radio astronomy made it possible to see the center of the Silver River Galaxy. There turned out to be a supermassive black hole there, Archer A'. Now we observe it regularly. But in the 1920s, it was the hidden band in miniature. Every time something important lies in a direction that is hard to observe, science finds a way around it. Radio instead of optics, X-rays instead of radio, gravitational waves instead of electromagnetic ones. The Grand Draw is the next iteration of the same story. Something important is hidden behind dust. We are learning to see through the dust. The process is slow, but it works. 40 years from discovery to a detailed map. That is not fast, but it is less than what it took for the center of the Silver River Galaxy. And one more parallel. The hidden band is not the only region of the sky with limited data. There are the so-called ecliptic crowns, regions that space telescopes can observe continuously because the day star never enters their field of view. The deepest data come from there. There are regions near the day star where ground-based telescopes cannot look during certain seasons. There are regions contaminated by satellite light, especially after the launch of sky mesh constellations. Thousands of satellites leave bright streaks across images, washing out distant galaxies. Every limitation creates its own blind spot. The hidden band is the largest of them, but not the only one. Astronomy is the science of seeing what is hard to see. Every new instrument opens a region that was once inaccessible. Every opened region contains surprises. The Grand Draw was a surprise in 1986. The Mason Cluster was a surprise in 1996. The Twin Drift Void was a surprise in 2017. Additional nodes in Starstreams Four were a surprise in 2023. The next surprise will probably come from the same region. From the 20% of the sky we are only just learning to see. It is worth speaking separately about methodology. How exactly do research scholars reconstruct the map of flows? The basic principle is simple. Every galaxy has two velocities. The first is Hubble velocity, caused by the expansion of the Cosmos Expanse. The farther away a galaxy is, the faster it recedes. This is Hubble's law, discovered in 1929. The second velocity is peculiar velocity, caused by local gravity. A galaxy may move toward a massive structure or away from a void, on top of the general expansion. To measure peculiar velocity, two things are needed: the distance to the galaxy and its redshift. Redshift is easy to measure from the spectrum. Distance is harder. The problem of cosmic distances is one of the fundamental ones in astronomy. There is no direct way to measure the distance to a faraway galaxy. What is needed are so-called standard candles, objects with known luminosity. For elliptical galaxies, the standard candle is the Faber-Jackson relation. The dispersion of stellar velocities correlates with luminosity. Measure the dispersion, get the luminosity, compare it with the apparent brightness, get the distance. For spiral galaxies, it is the Tully-Fisher relation. Rotation speed correlates with luminosity. Measure it from the width of the 21-centimeter line, get the distance. For distant galaxies, Type 1 supernovae. These explosions have nearly identical peak luminosities. Measure the brightness of the flash, Get the distance. Every method has an error margin. The errors accumulate. At distances of several hundred million light-years, the error in distance measurement can reach 10 to 15%. That is a lot, but enough to build a map of flows. Starstreams Four combines all these methods. 56,000 galaxies is not 56,000 perfectly measured points. It is 56,000 measurements with different precision, made by different methods, under different conditions. Statistical processing extracts the signal from the noise. The result is not a photograph, but a reconstruction. A flow map is a model built from data. The model can be refined with new data. It may turn out to be wrong in the details, but the overall picture, the coherent motion of galaxies toward a center of mass, is confirmed independently. And here an interesting question about the future arises. The Square Mile Array, a next-generation radio telescope being built in Suncoast and Westmark, should change the situation radically. Its sensitivity exceeds that of existing radio telescopes by hundreds of times. It will be able to see galaxies beyond the hidden band that are inaccessible now. But there are other projects as well. The Clara-Wren telescope, an optical survey telescope in Southridge, will begin operations in the coming years. It will scan the entire accessible sky every few nights. For the hidden band, this will not help. Optics do not pass through dust. But for the surrounding regions, it will provide unprecedented data. The Pathfinder Space Telescope, a Continental Space Agency project launched in 2023, is mapping the distribution of dark matter through gravitational lensing. It also cannot see directly through the hidden band, but it can estimate the mass behind it from the distortion of light from distant galaxies. Each new instrument adds a fragment to the puzzle. The full picture, if it is possible at all, will be assembled from many partial datasets. And there is one more aspect that is usually not discussed: the human factor. The Seven Wardens are not an abstract group. They are 7 specific people who, in the mid-80s, decided to measure the velocities of 400 galaxies. The work took years. The result was one paper, but that paper changed the understanding of cosmic dynamics. Maris van Elston spent several years at the Stonefield Array, systematically mapping the hidden band. This is not glamorous work. It is nights at the telescope, data processing, checking results. One structure, the Mason cluster, but it turned out to be the key to 44% of our speed. Daniel Roslin developed the method for reconstructing the velocity field that made it possible to discover the repeller. The method is mathematical, but behind it stand years of work on algorithms and testing on simulations. Science moves slowly not because research scholars are lazy. It moves slowly because every step requires verification. Every verification requires data, and every set of data requires time. 40 years from the first indication of an anomalous velocity to a detailed map with repellers and nodes. This is not a failure. It is the normal pace of fundamental science. And one more consideration: practical significance. Knowing where the Silver River Galaxy is flying has no practical application. We cannot change the galaxy's trajectory. We cannot stop or turn. A speed of 627 kilometers per second is a fact, not a problem. But understanding the structure of the Cosmos Expanse on large scales is the foundation of cosmology. If we do not know how matter is distributed around us, we cannot test models of dark matter and dark energy. If we do not know the velocity fields, we cannot calibrate the cosmic distance scale. The hidden band is not just a blank spot on the map. It is an uncertainty that affects all measurements in cosmology. Every time someone speaks about the Hubble constant or the fraction of dark matter, those numbers contain an error tied to the fact that we do not see 20% of the sky. Closing that error is one of the tasks of the next decade. Now for the open question: does the chain of attractions have an end, or will each next telescope reveal the next link? The Square Mile Array should close the hidden band, but if another structure on the scale of Norma lies behind it, the model will change again. If there is not, the principle of homogeneity will be confirmed. Either way, it is an answer. But which one exactly? We will know only when we look. In the next video, Strike, the mission that was supposed to shift an asteroid. The success criterion, 73 seconds of change in orbital period. The reality, 33 minutes, a difference of 25 times. What that means for the real defense of Earth Haven.